Hello and welcome to the 25th of our NASA Engineering and Safety Center Guidance, Navigation, and Control webcasts. I'm Neil Dennehy, the NASA Technical Fellow for Guidance, Navigation, and Control, and I'll be moderating this webcast. As I previously mentioned, the idea to have these hour-long webcasts originated several years ago with members of my NESC, GNC, TDT, technical discipline team, who thought that they would be a good way to broadly share their individual knowledge with the rest of the NASA GNC community of practice. We normally try to hold these GNC webcasts on the third Wednesday of every other month at this same time, 2 p.m. Eastern. I'm now very pleased to introduce today's speaker, Dr. Davin Swanson. Davin is the Director of the Control Analysis Department at the Aerospace Corporation in El Segundo, California. Among other things, Davin's department provides technical analyses in the areas of spacecraft attitude determination and control and payload pointing. He earned his Bachelor of Mechanical Engineering, MS, and PhD degrees from the Georgia Institute of Technology, and has worked at the Aerospace Corporation since 2003. His main areas of technical interest are spacecraft attitude determination, gimbaled payload line of sight determination and control, and payload jitter assessment. I would also like to point out that Davin has been a core member of my NESC, GNC, TDT for several years now. Davin's full bio can be found on the webcast registration page. Davin's talk today is entitled Fundamentals of Spacecraft Control-Structure Interaction. And now I would like to turn this webcast over to Davin.
Thanks, Neil. I appreciate the opportunity to do this webcast, to talk a little bit about control structure interaction, a topic I know a little bit about. I'm also looking forward to any questions that might come in during the presentation to answer a few of those at the end. So this presentation is intended for an audience of either junior GNC engineers who might not have a lot of exposure to control structure interaction, who might want to learn a little bit more about it, but have some GNC background, and some more senior staff that might want a little bit of a refresher, maybe that's been a few years since they've looked at this. So let's just jump right into it. What is control structure interaction? So I'll define what I mean by it first of all. It's defined as a detrimental closed loop coupling between structural nodes on a spacecraft and a feedback control system. And by detrimental, what we mean here could be either a performance impact or an actual instability of the control law. We separate this from an open loop response that causes unwanted behavior. This would be something like jitter in, say, a weather satellite that has an optical system, say a visible or infrared camera, and its response to disturbances on the vehicles that are well above the control bandwidths of the satellite, things like reaction wheels or steerable antennas, things like that. So let's talk about a little conceptual example first to kind of place us in what we're talking about. For GNC folks, these should be some pretty familiar plots. In the upper right, we've got a control block diagram of a typical satellite control system. We've got rigid body dynamics here, just rigid. And we have a PID controller using a rate gyro for feedback and feeding reaction wheels to follow an attitude command for the vehicle. And if we look here, we've got, if you look at the Bode plot and the Nichols plot on the left of the open loop transfer function, things look pretty good. The kind of magenta diamond there on the bottom left is a 6 dB, 30 degree gain and phase margin for the system. So we've got robust margins, well behaved. If you look at the step response, we have a nice little underdamped response that behaves well. Now, this is a rigid body model. If we were to then introduce flexible dynamics, and here I've just put in a couple little happy flex modes here. Now you can see things go a little crazy. We've lost our stability of the system. You can see the gain phase margins are out of whack there in the bottom left in the Nichols plot. And in our step response, we've got a nice unbounded, unstable response. So, in this case, if we had designed the system looking at only the rigid body dynamics, we would have been in trouble. But if we take the flex dynamics into account and we try to compensate them, here I've put a bending mode filter in the feedback loop. Here we've regained the stability of the system. The margins aren't as good. If you can look at the green in the lower left, we've got tighter margins as compared to the blue, which is the rigid body version. And you can see the step response doesn't look quite as good as it did in the rigid body case, but we're stable again. So this is just a quick kind of straightforward example of how flexible modes in the structure of a satellite can impact the stability and the performance of a control loop. That's a conceptual example, but let's talk about a real example, because this actually happens. That's why we're talking about it today. Hubble's a vehicle that everyone is familiar with to some extent. Early on in Hubble's life, it experienced a solar array flutter, which was some high amplitude oscillations of the science instruments due to interaction between the attitude control system on the vehicle and flexible modes in the solar array. And if you look at the picture of the solar array on the right there, you can just tell from looking at it, it's kind of a flexible structure. The array itself is flexible, and it's got a rather thin frame around it. And if you look at the plot on the left, you can see there is a period right at the 19.63 hour point where you've got some sort of disturbance that is interacting with the control loop on the vehicle and causing an oscillation. And this was so this wasn't a stability issue. The vehicle remained stable most of the time, but it did create a performance issue through these oscillations. And as it turns out, the level of oscillations they were seeing were unacceptable for science users. So something had to be done about this. So to fix it, the engineers working on Hubble, they decided that a software fix wasn't viable. Given the architecture of the control system on the vehicle, they couldn't fix this through control law tuning. So they sought a hardware fix. And to do this, they replaced the arrays with a stiffer design. You can look at the picture there on the left. You can, again, just by looking at it, you can see that that's a much stiffer design compared to the older one. And the supporting masts that connected the array to the vehicle, viscoelastic dampers were added to that mast in order to increase the damping of the modes that coupled the body in the solar array. So this was installed, and luckily in this case, on-orbit servicing was an option. These were in the days when the shuttle could go up and do servicing on Hubble, which they did many times. The vast majority of the vehicles up there, not including, for example, the International Space Station, on-orbit servicing just isn't an issue. So if this had happened on a vehicle where you couldn't service it on orbit, there would have been a real problem. So this is a real-world example that illustrates the importance of looking at control structures interaction when you're designing a control system for a satellite. So when there's some certain trends in modern spacecraft design going on, and it's making consideration of control structures interaction as a system level concern more and more important. This is not just a controls task. It's not just a structures task. It involves a lot of other subsystems on any satellite. It involves software. It involves the integration and test program. It could involve the payload if you have things that have to be controlled on a payload like pointing mirrors or filter wheels, things like that. It could involve the propulsion system and others. And these trends there are trends that have led to more structural flexibility in spacecraft. And the more flexibility you have in a spacecraft in general, the more you need to worry about control structure interaction. And you need to make sure you have a robust way to assess control structure interaction in your design. There's a movement towards lower cost launch options right now. There's more and more companies trying to build launch vehicles to get satellites on orbit. And one of the easiest ways to lower the cost of launch is to lower the weight of what you're launching. So that puts a focus on reducing the mass of the vehicles, or the payloads that the launchers are launching, the satellites themselves. We're seeing some vehicles with increasingly complex deployable payloads, things that unfold and unfurl on orbit, things like new types of solar arrays, antennas, other payloads, things like that. So when you have deployables, typically you've got a significant amount of flexibility in that. Also, as technology advances, there's more capable payloads being launched on satellites. These payloads require tighter pointing accuracy and knowledge, and that just makes the potential impacts from control structures interaction even greater. And then we've also got a case where we're seeing multiple payloads per vehicle. So there's many satellites that might have payloads built by multiple companies that are all integrated into one vehicle. And when you've got a supply chain and you've got different vendors building payloads to be hosted on the same vehicle, you have to be really careful about how you hand information back and forth and how you specify requirements for all of those different payloads. So the point here is that in order to handle CSI and make sure it doesn't bite you in the end, you really need a system level design process that identifies and comes up with a plan for resolving potential problems with control structures interaction early in a program, because the earlier you find and identify problems, the better. So what sorts of spacecraft features can drive CSI? This is just an example list of all the things that a controls or a structures engineer might need to worry about when they're looking at CSI for a vehicle. The propulsion system is one, thruster command profiles, fuel slosh, nonlinear effects of fuel moving around inside fuel tanks as the vehicle slews around. Valve timing and minimum impulse bits on thrusters can introduce nonlinear instabilities. Solar arrays, most satellites up there, well, all of them pretty much have solar arrays with some minor exceptions, and a lot of them have articulated arrays that have motors on them that move them to point at the sun to get ideal power on the array. The gimbal motors. Some arrays don't have slip rings, and as the vehicle goes through an orbit, the arrays have to rewind, do a full revolution in the opposite direction to come back to the home position. That can cause some issues because that's a higher rate than the normal solar array slew rates. Also, large deployable arrays can have inner panel hinges, and in some cases, these hinges there may be latches once the array deploys to latch the different panels in place, but in some cases they may just be held open with springs. So that can introduce flexibility in the system. Gimbal payloads, anything that moves around with a bearing, and that also includes reaction wheels. You can get stiction, cable wrap torques on a gimbal payload if you have wires or other interfaces that have to go across a gimbal. Imbalance of spinning rotors and reaction wheels or control moment gyros. Bearing noise, zero crossings, you can get stiction there. And then the instruments that we fly. I mentioned filter wheels before and scan mirrors. Also, infrared instruments sometimes have cryocoolers. Those introduce disturbances into the system. LiDARs have scanners. Spinning sensors can have imbalances. So these can all introduce issues that can affect the control system on the vehicle. So how would you address CSI as part of the system design process? It should be part of that normal spacecraft control design process. It should be considered all the way through from cradle to grave, as it were. Early on, when you're doing a conceptual design for a spacecraft, you can use that conceptual design and kind of an initial idea of what the vehicle is going to look like and what the control system, the ACS system, needs to do. That can drive a risk-based approach on how you would address CSI, both early and later in the program. The configuration of the spacecraft and the performance requirements for the ACS can drive what level of early assessment you need to do. If you have a very rigid vehicle that's kind of a flying brick and with very low ACS performance requirements, you might be able to skip a lot of the early first order analysis you might want to do otherwise. But if you have a very flexible vehicle with low frequency modes and or high performance requirements, that's a case where you probably should sharpen the pencil and do some early work to make sure that you've got a plan that can close once you've got full structural models available to do your control analysis. On the structural modeling side, and on later charts, I'm going to break this up a little bit into, I'll first address some structural modeling issues, and then I'll cover control analysis and control design. On the structural modeling side, iteration between the structural design and the control design is not uncommon. It's not uncommon for an early structure design to go through the control design process and the control designers to say, I've tried my best, but there's some modes in some places that aren't good. We need to tweak them, tweak the structure, try to move those modes around. That's not uncommon, so you should plan for it and know that could happen. Also, the level of model detail and the maturity of the model have a significant impact on the control analysis. If you have early models that are not grounded in any test data, you really should hold higher margins in your control design to make sure that later on, if you get surprises as you get a higher fidelity structural model, it won't break your system. On the control side, I mentioned before, there's some iteration between the structural modeling and design and the control design, but even just in the control design and analysis itself, that has an iterative process. A lot of control designers will start with a linear design and analysis using loop shaping or LQR, some sort of robust analysis to design a baseline control law. Then you want to run that in say a high fidelity time domain simulation with all the nonlinearities and high fidelity models of the vehicle, and make sure that you meet all your performance requirements. And then if you don't, you might go back to the linear design to tweak things, based on what you saw in your high fidelity results. So the other part here is that early on, if you do have a design where you think that control structure interaction might be a concern, early on in the conceptual design phase, and when you're doing kind of your first order control analysis, that's the time where if there's any modal requirements that need to be flowed to structures, do that early in the conceptual stage. You may have a minimum first mode frequency, or you may have a band of frequencies that you need to avoid. Say, if you know the bandwidth of your control law is going to be in a certain range, you certainly don't want any significant flexible modes in that frequency range. So again, this leads to an iterative system level design and analysis process. And really the point here in looking at this early and looking at it from the system level is to make sure you get early insight into this very system level effect of control structures interaction, and to avoid late changes which might be expensive or introduce significant schedule delays. So as I mentioned, I'll talk a little bit for a few slides about structural modeling first, and then I'll talk about control analysis. So structural modeling, you have a structure on a spacecraft, and a model needs to be built of that in order to analyze not just for controls, but for launch loads and some other effects. But the complexity of that model is often going to be driven by the complexity of the vehicle and what design phase you're in. So early on, you may not have a solid design of the vehicle. You might have to use things like lumped mass models. So treat the central body of the vehicle as a single rigid body. Maybe treat your solar arrays as several rigid bodies connected by hinge springs. Those are connected to the central body by a spring element. So it's a pretty high level, low fidelity assessments, but they could still give you some good insight into what frequencies your lowest modes might be. Now, if you've got a low bandwidth application and kind of a low performance application, that might be good enough. If you can convince yourself that the rest of the modes in the system are going to be significantly above your control bandwidth, and if you've got a design where you can get enough roll off in your control law, that might be enough for your full assessment. That's just a judgment call that you'll have to make given the situation of your program. Now, if you've got a more complex vehicle or higher performance systems, what we normally build are finite element models using tools like Nastran. And that will give us higher fidelity assessment of a greater number of modes in the system than just simple lumped mass, lumped parameter models. Now, in terms of the accuracy of these models, typically structural models, FEMs, you can get them to be pretty accurate for lower modes, but as the mode number goes up, they get less and less accurate, both in the frequency prediction and the mode shape prediction. So if you're building a lumped mass model, however, those are relatively straightforward. And if you understand the stiffnesses between these rigid bodies, say the stiffness of your solar array drive motor, which might be based on both the underlying structure it's attached to and also stiffness of bearings and other mechanical elements inside the drive. If you understand those stiffnesses well, then you can do a pretty good job of validating those models early on. Now, for an FEM, those are more complex models, and it's more complex to validate them and make sure that you've got appropriate accuracy. And I'll address that in the next few slides. Now, in all cases, when I've talked about lumped mass models and FEMs, those are linear models. But look out for nonlinearities. There are systems, and I have an example later on of how nonlinearities can cause control structures interaction that won't necessarily be caught by linear models. Now, combining multiple models is something you have to be careful about too. I mentioned before multiple payloads on a single spacecraft. If you've got multiple structural pieces that are being provided by different vendors to a single spacecraft, typically the vendors are the ones doing the modeling of each of those payloads. And it's not uncommon for those vendors to flow their models up to an integrator who's putting together the whole vehicle to do a system level analysis. And when you're doing that, when you're combining those models, interface modeling is critical. So how do you connect those models together? What is the compliance of the interface between all of those models? And in some cases where integrators don't want to build a full system model, these interfaces will be controlled by interface control documents that may specify maximum force and torque envelopes or maximum rate envelopes that PSDs that might be levied on a vendor to have to comply with. That's a less ideal situation. It makes the analysis simpler, but the highest fidelity result you'll get is from actually building an integrated model with the entire vehicle and all the parts and pieces combined. So here's a sample structural modeling plot. I like this one. This is from the International Space Station, and this shows how hairy these problems can get. This structural model is the plant for the ISS and the shuttle orbiter and an orbiter repair maneuver configuration. And this was a configuration that was proposed. If you look at the picture, the diagram on the upper right, you've got the shuttle that is attached to the space station using the shuttle arm, and you can see that arm on the lower right attaching the shuttle to the space station. And the station arm is an astronaut is attached to the end of the space station arm, and he is inspecting the heat shield on the bottom of the shuttle. And this was a proposed way to do heat shield inspection on orbit. So the plant here is coupled. You've got the space station coupled with the very thin compliant element, the shuttle arm. The space station coupled through the shuttle arm to the shuttle itself. So if you look at the frequency response plot on the left, you've got a section of rigid body modes on the left. Those are the modes that are created by the coupling of the shuttle to the space station through the shuttle arm itself. And then you've got a set of flex body modes at the higher frequencies. And those flex modes are in the shuttle and in the ISS themselves. So when you're trying to control that arm and maintain a given orientation between the shuttle and the station, look at how close. You only have about a dB of separation, or I'm sorry, a decade of separation between those rigid body mode peaks and the flexible body modes. And this is a case where normally what you'd want to do as a control designer is minimize your open loop gain in the flex body mode region, but maximize your gain in the rigid body mode region. And that does give you a whole lot of frequency range to play with. So this is kind of a complex system, and this is just another real example, like the Hubble one before, that shows how how hairy these things can get. So let's talk about damping a little bit. So when you do an FEM, for example, and you run a Nastran model to output the normal modes of a system, you get frequencies and mode shapes. And typically, the way you do that is you run a mass and stiffness matrix analysis, and there is no damping in that case. So you're looking at an undamped solution. Now, after the fact, once the controls guys get a processed model from the structures guys, we typically add damping to it because there is real damping in the system. Now, the thing that's done on all models is to add some modal damping, and that represents structural damping in the system. And structural damping captures energy that's dissipated in structure as there's flexible motion within that structure. And here, this is just a very quick, easy sample of a single mode in a system at different levels of damping. The blue, which has the highest peaks, is a 0.25% damping, and we go all the way up to 4% damping with the green. So you can see between the green 4% and the blue 0.25%, we've got over 20 dB of peaking, compared to the two. So that can really affect, it really affects the frequency response. So what type of damping level do you pick when you build a model for one of these systems? So as I mentioned before, the structural damping is usually implemented as a modal damping factor that's added to the entire structural model. And this modal damping factor, we talk about percent or fraction. It's a ratio of the critical damping level. So a zeta of 1 would be the critical damping level. A zeta of 0.0025 would be a 0.25% damping. So that's kind of the nomenclature we use. Now, what ratio to use is a subject of great philosophical discussion. If you ask 10 different controls or structures guys, what level of structural damping should you use? You'll probably get 10 different answers. You'll also probably get, well, it depends. So Neil and I looked for a little bit of data here when we were putting this package together, and the plot on the right, and I don't know, you folks watching online here, I don't know if this is an eye chart and you can actually see the numbers or not because it's pretty small, but this is from a NASA report from November 1971 entitled Structural Interaction with Control Systems. And this is focusing on launch vehicles, not satellites, but there's similarities. And the right-hand column looks at test measured damping ratios and estimated damping ratios for several vehicles. And if you squint, you might be able to see that among the test levels, you really don't see anything lower than 0.5%, 0.005. So most rules of thumb put a damping ratio between 0.25% and 0.5%. Some people say 1, some people say 0.1%. And it may depend on the type of vehicle and how many mechanisms and joints there are in the vehicle between the points that you're concerned about. But in general, it's better to use a lower number if you can get away with it because it's more conservative. If you've got a control design that closes with a 0.25% and your real system damping is closer to 0.5 or 1%, then the system's probably going to be fine with that higher level in reality. Now, one thing to point out here, this is kind of a special case, cryogenic systems. So systems that have to be at very low temperatures, say very sensitive IR focal planes or science instruments that have to be cooled down. We're talking to the tens of Kelvin level. Those can have damping ratios below 0.1%. When the structure gets really, really cold, the damping goes down. So those are cases where using a very low damping ratio might not be conservative at all. So you might want to think about that if you're working on a cryogenic system and do some evaluation of what the appropriate damping ratio would be. Now that was structural damping and applied as modal damping typically. Now mechanisms on vehicles will have damping inside themselves that I call discrete damping. So this isn't a uniform structural damping applied to the whole vehicle. This is damping just in a bearing or a hinge, or you could have a damper. You could have purpose-built damping elements added to a vehicle to intentionally increase the damping of targeted modes that you're having problems with. Now these are modeled separately from modal damping because they only affect a very specific part of the vehicle. And typically the damping ratios are higher than the structural damping ratios, and that's why you need to add them in and model them separately. It's not uncommon for a mechanism to have 3, 4, 5% damping across a bearing or a hinge. So not including these damping elements can lead to over-conservative models because you're assuming everything's 0.25% damping and you've got huge peaks on all of your modes. And it may drive you towards a less than ideal solution or doing more work than you have to. So the way these are usually implemented, again, the FEM models aren't really dealing with damping, they're dealing with mass and stiffness. And we add modal damping typically after the model data is processed into a form like a state space or a transfer function that the controls engineer can deal with. So often the discrete damping is added at that point. And the key thing there is your analysis model needs to have an input and an output at the physical location on the vehicle so that you can add those damping elements. So you may have a hinge on a vehicle, on a gimbaled payload, and all you really care about is whatever instrument is on the end of that gimbal relative to your gyro or your reaction wheel on the vehicle. But you need to have nodes at that hinge point on either side of the bearing so that you can put in a damping element in your model. It's not really something that you're going to observe physically in reality or that you're going to have any insight to, but you need access to it in the model to add that damping. So where do you have to worry about this? Examples of elements that could introduce additional damping. Bearings is one that I mentioned. Elastomeric mounts. Sometimes vibration-sensitive instruments might be mounted to elastomeric mounts to dampen vibration, as a sort of isolation system. Those have significant damping. Those need to be added. Dampers. Dampers have damping. And as I said, some systems will add discrete dampers specifically to knock down a mode. So those need to be modeled. Cables are a big source of damping. Spacecraft have lots of cables. They go across interfaces, across gimbaled interfaces between parts of the vehicles. And those dissipate a lot of energy when they get vibrating. So those can introduce damping as well. And hinges and latches. So that earlier Hubble example was a good example of where additional damping was added. They added the elastomeric damper to the mounting element that connected the solar array to the vehicle, and that way they were able to, I believe it was 3% damping or so on that specific mode. So that helped close the control design. Now, model reduction of the FEM. So if you build a full detailed finite element model of a spacecraft, it's normal for these models to have tens or hundreds of thousands of modes depending on the mesh size that's used. Now, this is kind of intractable for a controls engineer to use a system with that many states. So a reduced version has to be developed so that the control designer can design and analyze their control system in a tractable way, because it is an iterative process. So what you do here when you reduce the model is there's lots of modes in the system that have no contribution to anything that the GNC system is interested in. So, for example, one mode that you would be interested in on a spacecraft is the mode that goes between your, say, a rate gyro and a reaction wheel, because that rate gyro is providing direct feedback to the control system, which is sending a command to the reaction wheel. So that's a direct closed loop path there. So you want to represent that load path, and you want to make sure that all modes in the system that have significant content affecting those 2 points together are kept. But if you've got a mode that is, kind of twitching the end of a solar array, or moving a bracket on a launch lock on something, we don't care about that for GNC. So those modes can be removed without really reducing the fidelity of the control analysis. So how reduced do you make it? That's a judgment call, and that's often based on the tools that you have available, time constraints for simulation runs. If you want to do 5,000 Monte Carlo runs of your time domain sim, a structural model that has 100 modes versus 400 modes versus 1,000 modes, there's going to be a big difference in runtime. So you don't want to set yourself up with a model that's going to take you 4 years to do all of your simulation runs, to do your performance validation. So one method that's used to do this reduction is modal significance analysis. And I won't go into any details of that here. That's something that you can look up if you're interested in it. But that's a way to determine that influence of each mode in the system to each set of points of interest. It's like a gyro reaction wheel pair, as I mentioned. Now, it's also common to generate multiple of these reduced models. 2 are normal. You would get a kind of what I'd call here a reduced order model. They're both reduced order, but I'd say highly reduced order model, which has a relatively small number of modes that captures the, kind of an 80% solution. That's used in the design process where you have to iterate. You have to redesign your controller, rerun your frequency response, look at the disturbance rejection, look at your open loop transfer function, and then iterate as you tweak your controller. But then when you have a control design that you really want to evaluate, you need what I call an evaluation model, which is still reduced, but it has a larger number of modes than the reduced order model and is more accurate, and closer representation of the system compared to the full model. and that's used for the final performance evaluation. So you might have a subset of runs that you do with that large complex evaluation model to make sure that your system works in that in the full system configuration. So validation of the FEM model. So each of these models need to be validated. You need to make sure that you have a good model that you're using to do your control development. So this usually involves dynamic testing, and you perform dynamic testing and you compare the system response to the predictions that your model make. And one thing that we look at as a controls engineer is looking at the transfer functions of interest from those sensor actuator pairs, for example. And you look at it from your reduced model and the full model and your test data, and they should match pretty well. Now, when testing is done, typically a test model is generated, and that captures the system in a test configuration. So your normal model you use for your performance validation would be, say, the satellite free on orbit, but you're not testing the system on orbit. You're testing it on the ground, doing your dynamic testing. So your satellite might be floated on airbags, or it might be bolted to a launch adapter, and you want to have a model that represents that interface faithfully. Then you tune that test model that represents your test configuration to match your test data. And the changes you make to this as a structural engineer, the changes, what you should be trying to do is to enhance fidelity of specific areas of the physical system. Just kind of tweaking things or adding fudge factors here and there just to make the plots lay on top of each other isn't ideal. You want to try to have a physical reason why you're changing the model and why it matches better. So that's something to focus on when you're doing the model validation and the testing. And then once you've got the test model that matches pretty well, you've made changes to your test model that are physically based to match the test data. You then want to go back and make those same exact changes to your analysis model, that free on orbit model, and then iterate your analysis process with that new model. And this is part of that iteration that I've been talking about. Now, the type of testing that you do here, the type of structural testing, is based on the program risk posture and any cost and schedule constraints there are. The highest fidelity model you can do is a full vehicle modal test. You take the final vehicle and its preferably on-orbit configuration, deployed configuration. You have it in a high bay. You put shakers on it. You put accelerometers on it. You do full modal testing. But that's very expensive. It's time-consuming, and it comes very late in the program. You've already built your vehicle. Depending on the risk posture of the program and the cost and schedule constraints, it might be better to do some sub-assembly and assembly level testing early on. You might test a platform or a specific unit or a part of a payload. And that can still be very useful in finding and fixing problems early, because then you don't have to wait until that final full-up vehicle modal test at the end to make changes to your system. Now, you can do the best job in the world at validating your model, but there's going to be uncertainty. It's impossible to model a system perfectly. So that uncertainty needs to be captured in the control analysis process to make sure that the as-flown controller will work over a range of uncertainty, to make sure that you're not tuning to just one specific case that is highly likely to not be the case when you're on orbit. So things that you can tweak, you can take that structural model, you can change the level of modal damping, you can change the level of discrete damping, you can change mode amplitudes, you can move frequencies around, typically variations that you use 10 to 20% on modal frequencies. Some people go 25 or 30 depending on the vehicle and how early in the modeling phase you are, how much test data you have. 2 times variation on modal amplitudes is typical, but sometimes that's not used in lieu of just reducing the damping, because it has a simpler effect. And then in some systems that have high bandwidth controllers, we know that the accuracy of the structural models aren't as good as you get to higher frequencies, higher mode numbers. So sometimes there'll be a frequency dependent amplitude variation that's added that goes up as the frequency goes up. So if periodic testing is done, again, as I said before, the sub-assembly, assembly level testing, you can kind of march your uncertainty down as you do that testing and get a more and more accurate model as you progress in the design process. So here's an example for dynamic model uncertainty and how it can affect you. This is, again, an older example. This is the Gemini GINA program. This was used to practice rendezvous and docking and then large orbital change maneuvers in preparation for the Apollo program. And it used a Gemini capsule that was mated with an unmanned GINA booster at a docking interface. An early structural model predicted the first combined bending mode of this combined vehicle at 5 hertz. And the control designer at that point used a notch filter to knock down the response at that frequency and was able to get 6 dB of gain margin in their control law. But as test data came in and further analysis was done, turns out that mode, instead of at 5 hertz, was closer to 3 hertz. The notch filter, wouldn't have been in the right spot if this had been launched with the original design. That would have caused problems. And it turns out that at 3 hertz, the notch filter wasn't viable anymore. So they used a lead lag compensation to close the control design. So once they did a full ground test, they measured 3.6 hertz as that first mode frequency with 3% damping. And once on orbit, they measured a frequency of 4 hertz. So there's somewhere between the 3 and the 5. So that just goes to show that you've got to have a control design that closes across a range of frequencies, a range of structural model parameters. So control analysis techniques. So that was a little bit about structural modeling. So let's talk about controls, the other half of the problem here. So really there's no magic special sauce here. You use typical control design and analysis techniques, but using the flexible models incorporated into the plant model for your control design. And typically, one method that you use would be, let's start with linear analysis. Let's design a compensator, verify our rigid stability margins and our flexible stability margins. Then look at nonlinear analysis, maybe use a describing function analysis, or look at time domain simulations to look for interaction effects. These days, pretty much every control system is implemented in a computer, so discrete time impacts are important. Make sure you're modeling zero order holds, time delays, look for aliased modes if you have a sample data system, and make sure you have those factors included for uncertainty in your dynamic model. So this linear, nonlinear assessment, they're not uncoupled, and the control designer is going to iterate that. Looking at stability margins in the frequency domain, those impact time domain response. Lower phase margin means higher levels of oscillation in the time domain. You may see behaviors in the nonlinear sim, the high fidelity sim, that you might go back to the linear domain to do some loop shaping or some tweaking of your controller to account for those behaviors. And then another important thing here is that nonlinearities don't always hurt you. They can help you. They can introduce damping that's not reflected in the linear models. And that may improve performance and help you out. So you should look for that in your nonlinear time domain models as well. And it's always a good idea, I think, in your time domain sim to spot check your linear phase and gain margins. By altering the open loop gain or introducing time delays, you can find the point where your system just starts to go unstable, and you can kind of get a point check on your gain and phase margin, and those should match pretty well with your linear analysis. So here's a linear analysis example. This is from the example early on in the presentation. And the point here is that when I threw in my little compensator to compensate for the flex mode to go from the blue rigid body to the stable green flexible body response, there's more phase lag in the system with the flex modes. It can be difficult to retain and get back all of that stability margin once you add those flex modes to your model. And as I mentioned before, margins impact performance. You can see that in the step response. So the story here is your first cut control designs, especially if you're just looking at rigid models, you should make sure you have extra margin if possible to account for the fact that you may lose some when you start looking at flex. So I've got a little example here of nonlinear analysis, and this isn't time domain. This is a separate type of analysis, and we've been talking about flex modes, structural flex modes, but there's some structural interaction that can happen even in rigid body systems. So here we've got a single axis gimbal, and the block diagram shows a single axis gimbal with a bearing that has a nonlinear Dahl friction model, and the equations for that Dahl friction model are on the right there. The Dahl friction model is a nonlinear friction model that's time varying, and it models hysteresis in a bearing. And what can happen is friction can cause a system to limit cycle, and that is a nonlinear instability that doesn't blow up, but it causes a detrimental performance impact. This is something that you won't see in a pure linear analysis, but you might see in a time domain simulation. But there's a method called describing function analysis that you can use before building your high fidelity time domain simulation that may point towards a problem. So here's an example of a describing function. Again, this is very high level. I highly encourage people who are interested to go look up describing functions. I think it's a fantastic analysis tool that's underutilized. But here's a system where I've got the block diagram from the previous plot, previous chart with the control law, and what I'm doing here, if you look at the time to response plots on the left, the dashed red line is the input. So you can see I'm kind of goosing it. I'm giving it a little step command up to 0.05 degrees that lasts for a few seconds, and then I'm going back down to 0. So the point here is just to kind of goose the system and have it come back. You can see that does not look like a very well-behaved response in that upper left plot. And what happens here with describing functions is if you plot the closed loop frequency response of your system, of your linear system, which on a Nyquist plot, which is on the upper right, the blue line, you can calculate a describing function that represents that dull friction. Again, I won't go into the details here, but if you plot that describing function on that same Nyquist plot, which is in red, if there are intersections between that describing function and your closed loop response, that implies that there could be a limit cycle. And in this case, you can see with the original design here, we've got two intersections. And the bigger intersection is that lower one. The omega is at 0.11 hertz, and the amplitude is 0.034 degrees. And if you kind of eyeball the chart on the left and look at that periodic oscillation, it's at about 0.11 hertz, and the amplitude is about 0.034 degrees. So here I could do this describing function before I even run a time domain sim and go, oh, I might have a problem here. So in the bottom plot, what I've done is I've adjusted the integral gain of the controller. So the plant's exactly the same, the friction model is exactly the same. I've just tuned my controller a little bit. And now you can see that the intersections have gone away with the describing function, and I've got a better, more stable, and better behaved response in the time response on the bottom left. So I like describing functions. I think they're pretty cool. So I wanted to put that in as an example. So I've mentioned the iterative process before. This is my attempt to capture it in a plot. And the blue boxes sort of capture the system level structural modeling and control design process, and the yellow boxes capture iteration steps. And you start up at the upper left, where you're defining finite element model requirements, the modal requirements for your system. The model's developed, pair of reduced order models are built, and then you've got this modify control design iteration where you've got your flexible design, your linear control design with your flexible body models, high fidelity time domain performance simulations with your evaluation model. You go through that control design iteration loop. If that doesn't close, then you go through that lower modify modal requirements. Go back to the structures guys and say, sorry guys, you got to tweak the design to move the modes. And then throughout this whole process, throughout the whole program, as structural test data comes in that can update and make better accuracy models, then you've got to incorporate those and go through the iteration again. So I just wanted to kind of capture in one plot here that iterative process between controls and structures. So kind of in the tail end here of the presentation. So we've talked a lot about structural modeling and controls modeling, but as a system level design process, what should we look at? I said earlier, I've said several times, identifying potential risks early on is critical because you don't want to find these problems late and have to make structural changes or control architecture changes to deal with them. So if you can identify potential risks early, flow requirements to structures and mechanisms groups for modal requirements. Make sure you have strong, complete interface control documents that govern that interface between subsystems. Those should be put into place early. This all requires good back of the envelope control assessment early in the program. And if it's hard to nail down the specifics early, you at least should identify the areas that you should be concerned about and put TBRs in these interface control documents so that you can come back to later and say, hey, this is something we're going to have to look at, and we'll get back to it when we have more information. Identify required bandwidths of your control law. That'll drive your sample rates. That'll drive what type of flight computer you need, what type of hardware you might need. And the goal here, again, is to prevent late hardware changes. Those are expensive, they're time consuming, and no one wants to have to deal with that. Try to maintain plenty of stability margin in early control designs when you're looking at just rigid body models or maybe very early flexible models to allow for changes as model updates happen as test data is incorporated. Also, as you design your control laws, put hooks in there to make it easy to make late changes. One way to do this is to put some biquad filters in your linear control law with the coefficients zeroed out to set it to unity response. That way, you just have to change a flight software database instead of changing the flight software itself if you have to tweak things later. Make smart choices about placements of sensors and actuators. You want to have, say, like gyro or reaction wheels, star trackers, thrusters. You want these as close together as feasible, given other constraints on the system, or you want the structure between them as stiff as possible to minimize the chance that you'll get bad modes into your plant that you have to deal with. And pay close attention to modeling of joints and interfaces. This is where often a lot of the disconnect between structural models and test data comes up with bolted joints, gimbaled interfaces, hinges, bearings, things like that. So pay a lot of attention to those. So really the story here is this is an inherently cross-discipline process, and cooperation and coordination amongst everyone early on and throughout the program at a system level is key for mission. So, if you're a GNC engineer watching this, how should you deal with flexible modes? You have a model, you've got modes you have to deal with. Gain stabilization is your first thing that you want to try to do. That's preferable to phase stabilization. So gain stabilization basically means you're able to push all of your flexible modes above your crossover below 0 dB. It's more robust, but it generally requires more separation between your control bandwidth and your first flexible modes. Now, there may be cases where you have to phase stabilize. So that would mean that your modal frequencies might peak above 0, but you've got enough phase lead to stabilize your system. This could be a case where you have a system that just has very low structural modes, or you have very high performance requirements. You need high bandwidths. In this case, understanding the modal frequency variations and how the plant changes as you move those around, and understanding your time delays is critical. And here, be careful when you're considering notch filters to get gain stabilization, because slight changes in modal frequency can wreak havoc. That can poke the response above 0 dB pretty easily. Now, what stability margins should you have? There's no universally accepted standard for that. A lot of organizations have their own internal standards. The Goddard Gold Rule is one example, which I'll show in the next chart. But all programs should clearly state what those marginal requirements are for both rigid body and flexible modes in the ACS or GNC spec for the program, so that there's no ambiguity there. It's a good practice to hold additional margin if you can early in the program when the models are immature. And as a rule of thumb, as I mentioned before, gain stabilization should be mandated. Doesn't mean phase stabilization should be automatically discounted, but if you're going to phase stabilize, it should require a waiver or at a minimum extensive supporting analysis to show that the design closes. This is the Goddard Gold Rule for controller stability margins, and I'm not putting this forward saying everyone should use this. I'm just using this as an example of one of the things that's out there. Goddard says 6 dB gain margin, 30 degrees phase margin for rigid body modes, and 12 dB gain margin for flexible modes. And that inherently implies that those flexible modes should be gain stabilized because they should have 12 dB in margin. So this is one example. There's others out there. 6 dB, 30 degrees, 10 dB, 30 degrees, 10 dB, 45 degrees. Again, it's a philosophical discussion. More is better. So in summary, so this introduction to control structure interaction was intended to just provide a little bit of insight. It's hard to cover this in detail in a little less than an hour, but the intent here was to provide a little bit of insight and some context into the things you have to worry about in this important part of the design process. It's inherently a cross-discipline task. It involves controls, it involves structures, it involves flight software, avionics, propulsion, many more. So strong communication and coordination amongst all those subsystems are a key all the way through the program to make sure you've got a successful design. Early upfront work in the formulation of the mission and the conceptual design phase pays off. Having everyone's eyes open of what everyone else has to deal with and making sure things get flowed correctly at the high level will pay off in the end. And as I mentioned early on, there are some industry trends here, weight savings, vehicle complexity, things like that, that just make the need for a robust CSI assessment process more important. And this is a complex subdiscipline. And I've got a list of references here, and I believe that these charts will be available on the NESC Academy webpage after the webcast. So please feel free to take a look at these. And, you know, like I said, it's a topic that you could spend a lot of time digging into. And that's all I have. So, Neil, I'll hand it back over to you. Thanks.
Well, that was great, Davin. Thank you very much for coming today and sharing your knowledge and your insights and your perspectives on CSI. I think it was a good talk. You were right when you said it's a broad area to try to cover in 50 minutes, but I think you hit the high spots. You've given the folks references, and you know, I think they can follow up that way. So we've got some questions. It's almost the top of the hour, but I think we can do one or two.
Okay.
I think we got a challenging question here for you. It's the subject will give you a clue. It's entitled,
Okay.
When is enough enough? Okay? And it goes like this. It's a little long, but let me read it. The flight control / stability of the NASA EM-1 test flight of SLS Orion MPCV is depending on the first system bending modes being accurate enough. Planned ground vibration tests have very limited test objectives and little time to perform full model correlation. I think that's the key. To the extent that only the first low-frequency bending modes are somewhat measured and modeling accuracy or inaccuracy is determined. The question now is this really enough to assure control stability and identify realistic flight safety risk when we know that several more vibration modes are utilized in the flight control simulations? So that's there's a lot there. Okay.
I'll just address it at a very high level. But the you know, my way I would approach that, if the test plan is really only going to give you confidence in the first mode or two of the vehicle, and if you know that the next modes, mode 3, 4, 5, 6, are going to have impact on your system, and if you don't have a test plan in place to give you enough confidence that you're going to know those modes straight on, you've got to take that into account in that model uncertainty analysis that you do when you do your control design. So you might be able to put a different level of uncertainty that's mode dependent. You might only move those first modes a few percent or 5%, say, but you might still need to move those next few modes 10 or 20%. Run your control analysis and do an evaluation, and that's a judgment call, because depending on the outcome and depending on the margins you get and the performance you get, that might drive a case could be made for doing additional testing. So that's a case where you've got to look at the data and make a risk-based decision. So there's no easy decision to that, but you know, I would recommend as a controls GNC guy, you know, let the data drive your decision.
Yeah, I think we're touching on a trend we see here where there's, and it's in all the disciplines, not just GNC, but there's more and more dependence on the modeling and the analyses, right? And
testing is expensive.
Less testing because it's expensive and time consuming, and therefore you wonder about how well anchored your models are.
Right.
One thought I had, and I'd be interested in your thinking rebuttal on this or feedback on this, is maybe putting more energy into, you know, if there's pushback against doing the full up, all singing, all dancing modal testing, maybe focusing more at the submodel correlations, right? Doing more testing at the, like you talked about that and how important it is to the connections, right? We might have, in a, grossly speaking, in a 3, 4, 5 element full up model of a system, how you connect those
That's
3,
right.
4, 5 elements, and the coupling terms you use and compliances you use are critical. But maybe maybe that's where that's where you can do some variation of parameters. But maybe making sure at the one level down, you've got the best model and anchoring that model so that hopefully when you put it all together in the computer, you've got a better chance of getting the right answers. I also would think that it depends, if you're like you were cautioning against phase stabilization and being careful of the notch filters. I think
Mm-hmm.
that all could be could be more analytical evidence put on the side of doing more testing. If you're counting on notching something out or some more aggressive or not aggressive, but more complex filtering techniques, you really want to make sure you got the test data to justify that. So that's more ammunition, I think, to go push back for more testing. So
Yeah.
any thoughts on that?
Yeah, I think you're right. If a full up vehicle test isn't viable for whatever reason, schedule, cost, making sure you have the best data available at a subassembly level, and typically those tests are cheaper and they're easier to implement. They may even be able to be incorporated into a normal manufacturing flow to do spot checks and things like that. But like you said, you can increase the accuracy of all the various piece part models that you combine, but the uncertainty there is in the interface modeling, and I think that is actually a rich area of potential research for how do we model these interfaces. And there are some cases where you might not be taking credit for some advantages, like I mentioned earlier, cables. Cables introduce damping, and you might, if you're not accurately modeling the damping of those cables, you might be kind of shooting yourself in the foot, thinking that you've got much higher response when in actuality your system, once you put a cable between those two different structural models and you include that in the higher level model, that might knock down the response. So yeah, I think it's an interesting problem, and like I said, I think it's rich for research potential.
Yeah, I think your point being sometimes we elements of conservatism that we're not even aware of, right, in some of the
That's right.
modeling. And
Yeah, you don't want to stack worst on worst on worst, because then
right.
you put yourself in a box. Yeah.
So thank you for addressing those questions. I guess I'm going to wrap up by saying we are soliciting feedback on this particular webcast and also in general on the series of GNC webcasts. I just want to mention in general again that the webcast planning committee is always looking for ideas on future webcasts that you think would be of general interest to the GNC community of practice. So if you have ideas or suggestions for relevant GNC webcast topics, please contact me. So I'd like to say thank you for participating with us today, and I hope you can join us again at our next GNC webcast event, which will be in May, when Dr. Michael Dubey, he's my colleague within the NESC. He's the NASA Technical Fellow for Mechanical Systems. He will be briefing us on fundamentals of space mechanism lubrication for GNC engineers. So we look forward to hearing from Mike on that in May. Thanks again, Davin, for taking the time to put the presentation together. It was a thoughtful set of charts and raised a lot of issues. I think the list of references in particular will be good for people to pursue on their own. So thanks again for doing that. And I'll just say this completes today's NESC GNC webcast, and I'll say goodbye for now.